All right, guys, so we are doing 498. Let's start by doing the figure. So this is a fan, so the fan is going to require power. So let's say here, power here is 0.2 horsepower, okay? And then there is air going through the fan, so air. This is, we know T1 is equal to 535 Rankins. CP, okay, they give us CP 0.24 BTUs, LB Rankine. Okay. And this fan is going into the heat exchanger. So we go this way, this way. Okay, so now, so one, okay, 2 is all the way down, that's pretty strange. T2 equal to 528 Rankines. And then we know T5 is saturated vapor, and P5 equal P4. P4 is equal to 60 lbf inch square. We know this is a throttling valve, or just valve. And they tell you that at the beginning, this is saturated liquid. So this is 3. And you know that T3 is 115 Fahrenheit, and the mass flow 3 is 1.5 pounds per second. Okay, so if I show you my figure, basically, I hope I'm not missing anything, but this is what I have. Okay, yours probably looks about the same, no? Or actually, your drawing skills probably are much better than mine. But basically, I just copied the figure, no? So I find strength at 1, and then all the way to 2 is here. And then this is 3. That's confusing me a little bit. Okay, but let's see what they ask us over here. So from figure 498 shows 3 components. So the valve, the fan, and the heat exchanger of an air conditioning. Okay, system. Refrigerant 134. So I forgot to put on my figure here. This is refrigerant 134A. So we know the substance. Flows through a throttling valve and a heat exchanger while air flows through a fan, okay, and the same heat exchanger. Data for steady state operation are given on the figure. There is not a significant heat transfer between any of the components and the surrounding. Kinetic and potential energy are negligible. Modeling air as an ideal gas with CP equals 0.24 Rankines determine the mass flow rate of the air. Okay, so let's see. So basically they say that the heat assumptions here, or what they're telling you on the problem, is that none of the component is losing heat, that we can neglect kinetic and potential energy, that is steady state, so meaning this term over here is 0 because it's steady state. And what we need to find is the mass flow of air. So, air. All right, so there we go. So over here, my intuition. So like I was saying, this type of problems, there's generally two ways, two things that can happen. Is that you need to define a control volume open system for each one of the components, but sometimes you can combine some of the components. So in this case, since they don't give us any information in here, my first intuition would have been to create one control volume for each one, okay? But since here I don't know anything, my feeling is that let's select that our control volume is going to encompass, or is going to be enclosing the fan, so fan plot heat exchanger, okay? This is our control volume. So this is extremely important when you do the solution. You need to let me know what is your control volume. Otherwise I can take, is it just the valve? Is it just the heat exchanger? Is it just the fan? Is it the fan and the valve? No, there's multiple combinations, no? Okay, so now that I have it on the figure, you can say, so applying first principle of thermodynamics to control volume. Remember, this control volume is the one on top. So what is the general expression for the control volume? Is heat minus work, minus power, sorry. Then we had whatever goes inside our control volume. So what goes inside our control volume? Plus M1, but that will be M of air. Let me just call it M sub A now. What else is coming in? So H1, what else is coming in? M of the refrigerant, let me call it M dot sub R. This will be M sub R here. H4. Is it anything else coming in? Doesn't look like, no? Now there's two things coming out. So this should be equal to M dot of air T2 plus mass of refrigerant H5. I mean, I'll tell you why, but I was thinking ahead, but it should be H2, you're completely correct. It's because later on, we're gonna, this is an ideal substance, so this is gonna become CpT2, okay? But yeah, you're right. It should be H2 over here. So basically, what is one of the assumptions? They say that none of these components in these problems are assumed to lose any heat or to receive any heat. So really, it means this term over here is zero. Now, is it power into that system? Yes, it's the 0.2, no? We need to be careful with the sign convention, see what happens, but I just put the arrow. And basically, what do we need to solve here for the mass of air, no? All right? So let's say what would that give us over here? So this will give us mass of air. Let's factor out. Oops, I should have maybe, okay, doesn't matter. H1 minus H2. I'm doing some algebra already. And then let's say I'm going to have here the power. I move it to the right hand side. So I move this one to the left side. I move the power to the right hand side. So I have power plus M of refrigerant. And here we'll have H5 minus H4. Okay, so I hope that you remember this. If air is assumed as an ideal substance, what does that mean? That the change in enthalpy can be equal to what? Cp delta T, no? Okay, so I can really rewrite this term over here as mass flow of air, because it gives us a Cp over here, that's why I'm using it. Otherwise, you could use the tables, would be Cp T1 minus T2. Okay, we know T1, we know T2, we know Cp. And this will be equal to the power that is going into the fan plus mass flow of refrigerant, H5 minus H4. So we need to solve for the mass flow of air. So mass flow of air will be equal to power plus mass flow of refrigerant, H5 minus H4, divided by Cp, T1 minus T2. Okay, so imagine this problem that is quite complicated. I mean, probably complicated. But if you write this down, you show me that you understand the problem. So you probably get out of 10 points, probably 7 or 8 points out of 10. And we haven't done any numerical application yet, no? Okay? Okay, so somebody asked me, but now this is steady state. So steady state implies that it's conservation of mass. Conservation of mass means there's the same amount of mass coming in and coming out. So if you want, we could write over here, which is important as well. Let's see. So 64. So we know that steady state implies conservation of mass, and what we're going to have? We're going to have the mass flow of air is really equal to the mass flow 1 and mass flow 2, no? Okay, everything going through this line here will be the same. For the refrigerant, it's going to be even more. We should have m dot what? 3 equal m dot 4. Here we need to be careful because now, equal to m dot 5 is the same. Yeah, solve the figure. So this is what we have, which is basically what I did over here. When I wrote this equation, I already did the assumption, no? Yeah, so but I just, now we put it over here. Okay, so out of this equation, what do we need? We need to find H4, no? Yes? Okay, so let's go find H4 first, because that's really the reason why I'm doing this problem is for that I selected this problem. Okay, so H4, what is the component we're dealing over here? Is the valve. All right, so we're going to take the valve. I'm going to redo a sketch for the valve, but I'm going to do it in that direction. Doesn't matter. All right, this is our valve. So this will be our control volume. This is our new control volume. Let's say control volume 2. All right, this will be 3. This will be 4, no? Okay. So at 3, what do we know? We know two things. We know that it's saturated liquid. We know the temperature is 115 Fahrenheit, and this is not important, but the mass flow of air of 3 will be equal to the mass flow of refrigerant is 1.5 pounds per second. Okay, so you don't need to write it down all the time, but now we do the same thing. We're going to apply the first principle of thermodynamics to this control volume. Okay, so what is the general expression? Will be Q dot minus power plus what? Plus m dot of refrigerant is going in times H3 will be equal to what? Mass flow of refrigerant H4. Now, in this figure, is it any heat loss or gain by the valve? No, everything comes from the figure, no? If it's not on the figure, it's not happening. Is there any power that needs to be provided or given by the valve? No. So that means right away that when you have a valve, when you go through a valve, you're going to have the enthalpy throughout the valve is conserved. Okay? So that means that if we find the enthalpy before at the entrance of the valve, that should be the same as the enthalpy at the exit of the valve. And remember that from the tables, every time we look for something, we need to know two things, no? Do we know two things here at point 3? We know the state, we know the temperature. So we should be able to find what? H3, which would be equal to H4, no? All right? So, all right, let's go to the tables. So I'm going to pause over here when I go to the tables, so we don't waste any time. Okay, so if you go to the textbook, on the tables, we use refrigerant 134A, and we know the state is what? Saturated liquid. So that means, what does that mean? It means it's going to be on the curve on the left-hand side, no? So that means that on the table, we need to look for the values of fluid, okay? U sub F, H sub F, all right? So let me, oh, I think it's big enough on the screen. Is it big enough on the screen? Can you see it? Okay. What else do we know? We know the temperature. So we need to look at this column over here, saturated liquid for H sub F, and the temperature, this one is in Fahrenheit, so maybe we need to transform. Oh, no, the temperature T3 is given in Fahrenheit, that is 115. So this column for 115, we are lucky, we have the value here, would be what? 49.63. Okay? Again, practice with the tables, otherwise you're going to have problems. So I'm going to write down from table A10, table A10E at saturated liquid, you need to know two things, and T3 equal to 115 Fahrenheit. You have H3 will be equal to H4, that is equal to 49.63 BTU LP. Okay, so once I come here, this is what I have. H3 equal H4. All right, and you see, when I say that I come to table A2A, you're going to have to tell me that you know two things, no? We know that it's a saturated liquid, so we know we need to look at the H sub F, and we know at the temperature. All right, so out of this equation, we know H4. T1 is given to us, so we don't need it. CP is given to us. T2 is given to us, no? Okay, so we know H4. What do we need to find? H5, no? Do we know two things are H5? Looks like. We know saturated vapor, and this is telling us that P5 equal to P4, but they are kind enough to give us already P4, no? All right, so let's find here H5. So what do we know at H5? So I don't think we need to do anything. So H5, we know that it's a saturated vapor. We also know that P5 equal to P4, and we know that P4 is equal to 60 lbf inch square. Okay, and the substance is still R134. So that means that what is the state? Saturated vapor, This is 60, so probably we have two choices to go to two tables. I don't know. So this is for the temperature. If we are lucky enough, we have 60 here, but this is 60.125. So probably the value we're going to have to find will be close to 27.28, but this is not 60. So let's see if there is a table. This one here, table 11E. Okay. We know the pressure is 60. Are we lucky enough to have a 60? Yes, no? Right? 60 and is vapor. So we need to look at the H sub gas this time. Do you know the difference between F and gas? It's on the side of the curve, no? If you remember, I told you that you could bring, what would that be? That you could have this page with you. So if it's on this side of the curve, this is saturated liquid. If it's on this side of the curve, this is saturated vapor, no? All right. Okay, so here we are on this. So let me not lose track. We are at 60. So H sub 5 will be at H sub G. Oh, so it's a big difference here because, yeah, I was looking on the other side. So that gives us an H sub G of, did I take the correct one or? Looks like, no? So from table 11E, you could come here, but otherwise, let's see, they have a table A12E, which should be the superheated. And here they had 60. What do they have? What do they have here for the saturation? H108.72. Is that the same value we had on the other side? So you can go to either table 812E or 11E. All right. But I think it will make more sense to go to 11E. Table 11E at 60 is 108.72. Okay. That way we double check. All right. So from table A11E, H sub 5 would be equal to H sub gas equal to 108.72 BTU LB. Okay, so I think we have everything, no? So now from this equation, it looks like we have the power. We know the mass flow of R is given to us to be equal to 1.5 lb seconds. We know the H5, H4, CP, T1, and T2. So let's just be careful with the units and see what happens. All right, so recalling the equation. M dot sub A equal to power plus M sub R H5 minus H4 divided by CP T1 minus T2. Okay, here I'm going to do a little sketch because I need it personally. The units, oops, sorry, let me come here. So I was rewriting that equation. So remember, the textbook notation for the units is what? Work given or power given is positive, and power going in will be negative, no? All right, so they were right on the book. So let's see what happens here with the units. Let's write them down so we know this. We go to the next page. This will be what? I think was equal to 0.2 horsepower. So instead of doing everything here, so this is 0.2. So it should be what? If it's going in, it should be negative, no? Horsepower. What is the unit transformation to horsepower to BTUs? I also tell you that I think you should bring this page to every single class. All right, the one with these conversion factors. So do we have it somewhere? So 1 horsepower is 2,545. So which one do we need to use, the BTUs or the pound force? Everything else in BTUs. So I think we're going to need this one in BTUs. Okay, so see what happened. So here we have 2,545 BTU hour divided by 1 horsepower. Okay, did they ask us? Did somebody pay attention? Oh, I can check here on the solution. I can do some cheating. So they want the solution in per second. Okay. So now I need to transform these hours probably into seconds. Okay. So now the other unit transformation we need over here will be, so the 1 hour is dividing. We need to do 1 hour multiplying will be 3,600 seconds. Okay, so if you do the numerical application, what do you get for this value? 0.1413. Okay, negative, no? And this will now, we have the hours, so this one cancel, hours cancel, so we have 2 BTUs per second, no? Yeah? We didn't do anything wrong. This should be BTUs per second. I think it makes sense. Because now, hopefully, this will cancel. So we have this. Now, let's move to the right. What is M sub R? So in the problem, N sub R is equal to M dot 3, and that was given to us to be equal to 1.5 pounds per second. Okay, so H5 we just calculated to be equal to 108.72 BTULB. H of 4 is 49.63 BTUs LB, and CP is also given to us, is 0.24 BTUs per pound degree Rankine. What else we need? T1 is 535 Rankines, and T2 is 528 Rankines, no? So we can go and substitute. So this will give us that the mass flow of air, and the equation right here on top will give us what? So we just calculate this one to be minus 0.1413 BTUs per second plus MR is 1.5 LB second times H5 108.72 minus 49.63, and this is BTUs LB, no? Should be. Yeah, BTUs LB, so everything makes sense. We end up with BTUs per second, no? Again, which is what I wanted to check. All this divided by 0.24 BTUs LB Rankines times T1 535 minus 528. And this would be Rankines. So you see the Rankines will cancel out, the BTUs will cancel out, the BTUs will cancel out. So sorry, so BTUs, BTU, yeah, cancel out with this one, and we are left over with pounds, and the Rankines pounds per second. Because this pounds goes up, pounds per second, and this one, here what happened? Why did we do something wrong here with the units? So this MR is pound per second, BTUs per LB. Oh, yeah, this cancel, but this one will go up, no? So we're good. We're good. So what do you get if you do that? Hopefully we get the same answer as they did over here. I think we have. I guess you will get 51.9. What do you get?
I got 52.6, but I may have rounded somewhere.
Okay, can somebody do it so I can?
I got 52.67.
52.67. Let's do 52.67. Okay. I mean, let's see if they did the same thing as we did, because I think you can also do it with the tables. Because I don't think you need to do the assumption of CP. Did they do the assumption of CP here? Yeah, they did the same assumption, so. I mean, same values. So, somebody has a problem using a calculator here, maybe, no?
They have it as -2 horsepower and 1.2.
Yeah.
No, now ours is -0.1413 because we already did this unit transformation. So all this time here.
Yeah, but like the starting horsepower for us was 0.2. Theirs is.
Oh, that is the difference. So did I do the mistake? Was it 2 or 0.2? 0.2. So okay. I don't know. That's what I'm telling you. Don't trust that much the solution manuals, no? Okay? So anyway, what we have done is consistent, no? And this is what I care about the procedure. So let's do another problem. Okay, so guys, please copy this figure, all right? And then I will give you the steps in order to solve it, but you will have to solve it on your own. Okay, so for the first part, you need to find power of A, no? Power required by A. So for this one, what are you going to do? You're going to take, this is what I was trying to do before. What will be your control volume? Control volume 1 would be your compressor. Okay? So if you use this control volume, what would be the first principle of thermodynamics? Would be Q minus power of A plus M. What is the substance here is air, so let's say M sub A H1 will be equal to M sub A H2, no? So in this case, they say to neglect all the heat transfers. So you will have that power of A will be equal to what? Mass flow of air, H1 minus H2. Okay, so leave some space because you're going to have to find, probably from the tables, H1 and H2, no? Okay? All right. We do exactly the same thing in order to find the power of B. You're going to take a new control volume. So your new control volume is going to be the compressor B. Again, you're going to have what? 3, 4. This will be your control volume. So for control volume 2, you write down your first principle of thermodynamics will be Q dot minus work power B plus M dot of, this is still the air, H3 will be equal to mass flow of air, H4. And as before, heat transfer is 0. So you find that the power required to run the compressor will be equal to the mass flow of air, H3 minus H4. Okay, and the last thing they ask us is what? To find the mass flow of water, is that correct? Let's see. The mass flow of water in kilograms per second. All right, so maybe now from here will be labeled clear. Now what do you need to do? What should be your control volume? Probably your control volume now, you pick the control volume to be the heat exchanger, no? Yeah? So let's say so to find the mass flow of water, you do the heat exchanger. So what do we have? 2, 3, 5, 6. You have control volume 3. So for control volume 3, we have Q dot minus power plus mass flow of air, H2, plus mass flow of water, H5, equal to the mass flow of air leaving, H3, plus the mass flow of water, H6. No heat transfer, no power. So this is going to give us mass flow of air, let's see, H2 minus H3 equal to mass flow of water, H6 minus H5. So this will give us that the mass flow of water is equal to mass flow of air, H2 minus H3 divided by H6 minus H5. I mean, I know I went a bit fast, but oops, sorry. But I just went through the steps, no? Do they make sense? Yes? So you see, I mean, here without giving any value, if you put that on an exam, you show me that you understand the material, you will have probably 7 to 8 points without even doing a single looking for a value, no? So let's say you can find the values now in the next 60 minutes. So you need to go to the tables. That's the difficult part, guys. If you don't practice to go to the tables, you're not going to do it the day of the exam, I'll tell you right now. So go ahead and use the tables. Okay, guys, so you need to, I want you as a practice to go on your own and find all the values on the tables. And in order to check your answer, I give you the values here, I give you the answers. But you need to go and practice. It's